PowerPoint, somebody was asking about if I'm going to send these ones. Yes. If you have not been getting them through your email, please let me know so that I make sure that you do get them. I have been just sending them through a group email for the entire cohort. So maybe in case somebody gets left out. Yeah, so please let me know. All right, let me take one note here. Has anybody else not been getting the emails? Because I will make another email tonight and send everything from previous classes. All right, quite a few of you. Apparently the group email is not working out well. Yeah, definitely check the spam folder, but I will send another one. I'll create a whole new email to everyone. I will send it with all of the PowerPoints from last week and this week. Yeah, so definitely check your spam folders, but I'll send another one just to make sure everybody gets it. All right, so tonight's just review, guys. You can breathe a little bit. I know week 2, how are we reviewing stuff? But week 1's rather heavy. It really was. And then you had another heavy session yesterday in 300. So tonight is literally just reviewing everything that we went over in week 1 for the most part. I did go through your quizzes and see where the areas of weakness were, which we're going to hit on a couple of those, but you guys did really good in this class. There were literally, I think, only 4 questions that it seemed like the group struggled with. And it's probably just wording. Our questions are sometimes tricky. You may notice that you really have to read them carefully before you select the answer. So I will go over a few of those things as well. But what I would like you to do is just go ahead and change your chats directly to me. That way you're having to think a little bit and not relying on anyone else's answers. Just kind of test your knowledge. Nothing against you if you get a wrong answer. Don't worry about it. Try it. See what you come up with. We want to start making that muscle memory happen. And hopefully you'll see that some of this stuff now is starting to get a little easier. And anybody that didn't hear at the beginning of class, just make sure you have either a calculator or your cell phone close by. There's a couple easy problems we're going to work on. But other than that, nothing major. All right, so we're going to start off with talking about that atom. All right, remember we have electrons that are orbiting that nucleus. They're going to be spinning on their own axis, and the nucleus itself is spinning on its own axis. What do we find in that nucleus? All right, protons and neutrons, you got it. Good job. I'm just writing down somebody's email. Give me 1 second here. Make sure too in Moodle that your guys' email is updated. Like if you change it or if you change your phone number, because that's what we go to get your information. So if you guys ever change that, make sure you go into Moodle and update it. All right, so protons and neutrons are going to be found within the nucleus, electrons orbiting the nucleus. What is the atomic mass number made up of? This is where we use the word mass and turn it into math, meaning we have to add 2 things together. What is the atomic mass number made up of? Here you go, protons and neutrons. Let's take the word mass and just in your mind, when you hear mass, think of math. We need to add 2 things together. It is going to be protons plus the neutrons. How about the atomic number now? Process of elimination. This one will be easy. You got it. Number of protons. Electrons. How many electrons should we see orbiting a nucleus? What does those electrons match to make that atom stable? You got it. Same number of protons. Yes. So atomic number is going to be the number of protons, and the number of protons will equal the number of electrons orbiting. That's what makes the element stable. What type of mass number does MR active nuclei have? Yes, odd atomic mass. This one tripped you guys up this past week on your quiz because we used some fancy words and used a special sequence that we can run. And everybody, I think, got tripped up with the wording instead of just looking at the answers and finding the element that had the atomic mass number that was odd. That's all it was going to take. But again, you got to dissect those questions down and be like, I don't need this information. I don't need this information. So odd atomic mass number. The MR active nuclei is going to have that odd number. It can be any combination of protons, neutrons in that nucleus, but it has to be an odd sum. And because of this odd number, they can be influenced by that external magnetic field. That's why we utilize them. Why do we love hydrogen so much? What makes hydrogen so great for us? It is abundant. And when we say it's abundant, what tissue in the body specifically are we imaging? There's two types of tissue that we image that the primary element is hydrogen. What are those two types of tissue? Good. So it's going to be our fat and our fluids, whether it's cerebral spinal fluid, whether it's, just water content within the body from edema or inflammation, but fat and fluid are the two types of contrast. And those primary elements that are contained in both of those are going to be our hydrogen. Hydrogen nucleus, as you know, contains a single proton. So therefore it has a pretty large magnetic moment. So it's going to be spinning on its own axis like a little Earth. Always just kind of visualize it as a little Earth spinning. Going to have that north and south pole just the same as the Earth does. What does Faraday's law state? A little bit more wordy, I guess, here. You can try to make it a short answer, but it's a little harder to answer easily. But what does it state? Good. Good. You guys got it. Some of you were able to actually bring it down a little bit easier to answer, but Faraday's law states that a changing magnetic field will induce voltage. MR signal, of course, is a small electrical current that's going to be induced in that coil that we use by the precession of that net magnetization vector during that resonance. This is exactly why Faraday's law is so important, where that changing magnetic field is occurring. We're going to be able to induce that voltage within that actual coil. What properties does a magnetic vector possess? There's two properties that you should be fairly confident in answering when we talk about a magnetic vector. What does it possess? These two properties. Good. Magnitude and strength are the same thing in direction. So you could say magnitude and direction, you could say strength and direction. Those would be correct. When we are looking at the image previously here that you can see, it's represented by the arrow. Okay, that arrow is the representation of that magnetic vector. The direction it is pointing, of course, is representing the direction, and then the length of it is the strength or the magnitude of it. So again, represented by that arrow, the direction it points is the direction of that magnetic moment. Length of the arrow is the size or the magnitude or strength of it. How are hydrogen protons aligned outside of B0? And everybody should be at the point they're sick of me asking this already. I know you guys know this. How are they aligned? You got it. They are randomly aligned. Outside of a magnetic field in the everyday environment, they are obviously repelling each other. They are all pointing different directions. I used to say this is like when you're at a wedding and the song I Want to Dance with Somebody comes on. Everybody's dancing and moving, but they're all going different directions. And then B0 decides it's going to put on the electric slide. And most everybody lines up the same way. Of course, you always have the oddballs facing the wrong direction, but that's what happens when you put a body into the scanner. Most of them are going to align with, whereas some are going to align against. So we have protons that are going to align with and align against B0. What are the other names we would use for the ones that align with B0? Besides just saying they align with, what are the names of those hydrogen spins that are aligning with it? Good. Low energy, parallel, and spin up. Good job. So low energy, parallel, spin up. And what are the names of the hydrogen protons that are resisting that alignment? They're opposing it. What are the other names? High energy, anti-parallel, and spin down. Good. And again, you do need to know all of those. Your registry can use any of those to describe the alignment. So again, parallel, spin up, and low energy are the ones that are aligning with B0. Anti-parallel, spin down, and high energy are aligning against B0. Looking at this image here, what would our net magnetization vector be? Remember, net magnetization vector is just the excess spin up hydrogen protons, the summation of what's left over. So this is 1. Your net magnetization vector here is 1. There is only 1 extra spin up hydrogen proton remaining after all of these cancel each other out. So 1 is your NMV. What is thermal equilibrium? What is your definition of thermal equilibrium? All right, I can see this is an area we're still struggling with a little bit. Thermal equilibrium, it's simply when you place the patient into a magnetic field and those hydrogen protons settle, whether it's parallel or anti-parallel, once they settle into whichever direction they choose, that is thermal equilibrium. Okay, so once the hydrogen protons settle into parallel or anti-parallel alignment, that is thermal equilibrium. So here is the answer. Whenever they have settled into their state, it's going to be influenced by, of course, our magnetic field strength. If we have a 1.5 Tesla scanner, we're going to have, say, maybe an NMV of 10, and then you go to a 3 Tesla scanner, well, now you're going to have an NMV of 20. We're going to have twice as much, which is going to give us more signal, which is fantastic. It's also influenced by the patient's body temperature, but we can do nothing about that. We're not going to put our patient on ice and we're not going to warm them up to make things work the way we want. So we can't do anything about that. All right. How do we find the net magnetization vector now? We just practiced one a moment ago. What did we do? All right, good. Guys are on it. So nuclei of opposite energy are going to cancel each other out. They do not contribute to the NMV at all. We do not get signal from them at all. As you know, there's always going to be a few extra low energy nuclei that are not going to get canceled out. That is the NMV. That is going to be represented when you see our graphs, usually by M0. When you are looking at the image here, what is our net magnetization vector? You can see everything canceled out for you right there. So what is the NMV? Perfect. It is 3. Easy, right? When is the only time, or I guess really it's all the time, but when is the NMV 0? When is your net magnetization vector 0? So net magnetization vector is 0 when you are outside of a magnetic field. There's no parallel or anti-parallel alignment. They're all in opposition. Okay, so outside of a magnetic field, as you are right now, the NMV is 0. Okay, so only whenever the patient is placed into the magnetic field are you going to have parallel and anti-parallel alignment. That's the only time you can calculate an NMV. Outside of the magnetic field, remember those hydrogen protons are wanting to dance with somebody, they're all hanging out different directions. There's no NMV. They all cancel each other out. Why do we want a strong NMV? Why do we care so much that we have a strong NMV? You got it. Signal. Everything in MRI is about signal. If you haven't figured it out yet, you're going to this module, but our goal is to have the best signal we can. Stronger signal gives us the best image we can possibly have. So we want to have that signal. So again, the only way we can usually create a larger NMV is by that magnetic field strength, going from that 1.5 to the 3 Tesla, or even a 0.3 to a 1.5, either way, just increasing field strength is going to give us a stronger NMV. What is precession? This is known as the secondary spin of our magnetic moments around B0. This is also referred to as a wobble. You will hear a lot of people call this a wobble. It's almost like a top. If you ever, as a kid, was playing with the top and you do the spin and you watch it start to wobble side to side, same concept. So that's how it kind of got the name wobble. The spin is just a tumbling motion through space that our MR active nuclei possess. Okay, that's without the external magnetic field, but the influence of our external magnetic field is going to cause this secondary spin. That is what's going to lead to precession. Yes, secondary spin from the magnetic field. What is the precessional path? It's an easy one. It is a circular path. You're right. So path, direction of spin, good. The path that the spin precesses around B0. There we go. Good. So it is a circular path that magnetic moment is going to follow around B0. So remember, when it's spinning on its own axis, it's like an Earth. It's not doing that wobble. Okay, it's not doing that. You put it into the magnetic field. Now we have this precessional path that's happening because it's starting to do that little wobble around it. So precessional path is that secondary spin path. All right. What is precessional frequency? How fast it spins. Good. The rate at which it's going. The speed at which it precesses. Good. Yeah, so this is the speed at which that is precessing around B0. Precessional frequency is always going to be affected by that magnetic field strength. Larger the field strength, the faster it precesses. Okay, so at 1.5, it's precessing at a certain rate. At 3 Tesla, it's double. Okay, it's going to precess even faster. And that's why it's important to calculate that precessional frequency so our RF can match that. Larmor equation for precessional frequency. Again, this number will be ingrained in your mind forever. 42.58 megahertz per Tesla is our gyromagnetic ratio of hydrogen. This is what we use to calculate what that precessional frequency or resonant frequency is going to be. Who knows the precessional frequency of a 3 Tesla scanner? So remember, this is going to be your gyromagnetic ratio times your field strength. So 42.58 times your 3. What is it going to give you? Give everybody a moment. That way, if somebody's actually calculating it out, because you want to be able to do this pretty easily. The resonant frequency or precessional frequency at a 3 Tesla scanner is what? I'm just giving a minute because I know some people are still working on it. All right, most of you are in the correct ballpark, and that's all that matters right now is that you know how to do that calculation. So resonant frequency is going to be 127.74 megahertz. Okay, so remember, gyromagnetic ratio times your field strength will give you your answer. Let's try another one. Let's do a 1.5 Tesla scanner. Yeah, don't worry about rounding right now. As long as you are in the correct ballpark, you know that you know how to do the problem, and that's all that matters. All right, I think most everybody's got their answer in from what it looks like. And most of you got it correct. All right, I don't think I saw one wrong answer come by. 63.87 megahertz. So now that you've done that, easy one. What is the gyromagnetic ratio of hydrogen? After doing 2 problems, everybody should get this correct, right? And you are. I love it. See, you guys know stuff. You should be proud of yourselves. You know it. You got it. It is 42.58 megahertz per Tesla. Excellent. All right. Let's jump back to resonance for a minute. So the exchange of energy between 2 systems at a specific frequency. Okay, this is what's going to allow resonance to occur. This is why matching that precessional frequency of the hydrogen spins with your RF pulse is important because guess what? As relaxation starts to occur and the tissue starts to give off that energy and we start to receive that signal, it's at the same frequency. So those frequencies have to match all the way across. If we deliver an RF pulse at the specific frequency, the matter absorbs it, it resonates, and then we will be able to receive the signal at that same frequency. And this is why tissue heating occurs. There's a laugh there. It's sorry. Somebody's comment me off guard there. When you guys start sending me poop emojis, that's when I know you're all done. Because every module, somebody starts sending me poop emojis at some point. So I always look for those. If we haven't gotten that far yet, we're doing good. Two things that occur when we turn on an RF pulse at that Larmor frequency. NMV moves into the transverse plane, flips 90 degrees into the transverse plane. All of our spins start precessing in phase. So they are all at their exact same location within their precessional path. So again, it's like all those watch faces. Say you have 10 watch faces and they're all pointing to noon at the exact same time. That is what's going to produce that strong signal. We need that moment. We need it 90 degrees into the XY plane. We need all of those spins at the exact same place in their precessional path. That is where signal comes from. All right, so here's just a diagram showing what's happening. Nucleus, enter your patient into the bore of the scanner. Hydrogen proton starts wobbling around B0. It's starting to do its little precessing that's happening. Hit it with an RF pulse. What happens? Tips 90 degrees into this XY plane. Okay, this is the perpendicular plane. So it's going to tip into that plane. That's where we are signal rich. Okay. If we are 90 degrees, this is where we achieve the most signal. At that time, when we knock the hydrogen spins into the XY plane, all of those hydrogen protons come together. Okay. Then they're going to all be spinning at the exact same place in their precessional path. Turn off the RF pulse. Relaxation starts to occur not only back to the B0 axis, the Z axis, but those spins start to go out of phase with each other. So remember, they're magnetic, they repel each other. So some will speed up, some will slow down, and they'll all be pointing different directions. They'll all be at different locations in their precessional path. This is where signal is weak. As they spread out further, less and less signal is going to be acquired. As the NMV relaxes further back away from that XY plane, less signal. Okay, so we want everything at the exact same point in their precessional path so that we have them all in unison. We want them all perpendicular to that B0 axis, that Z axis. So when we talk about the patient, and we've said it probably 50 times between last week and this week, place them into the scanner. Most hydrogen spins are going to align with B0. Some will align against it, but always a few more will align with. Excess spin up hydrogen protons are going to be your NMV. Okay, anything left over that did not cancel out is your NMV. Again, magnetic field strength is your determining factor of this as to how strong that NMV is going to be. RF pulse sent into the patient causes the spins to excite, tip into that XY plane. Signals produced immediately after that RF is turned off. This signal that is first produced is called a free induction decay signal. So the very first signal produced after an excitation pulse, the 90-degree excitation pulse, is known as a free induction decay. You should know this. Going forward for the rest of this module, the free induction decay does not usually contribute to the signal that we read out. It does not contribute to our echo. But when you go into module 4, into advanced physics, we do actually start using the free induction decay in some of the advanced sequences. But as of right now, this is the first signal produced from the excitation pulse at the beginning of the pulse sequence. So when the RF pulse is turned off, you're going to see this in your pulse sequence diagram. RF pulse is turned off. You have all of this signal. Look how quickly it's decaying. Okay, we're losing signal rapidly because those spins are going out of phase with each other. And if we draw a line, I'm not the best at drawing, guys. This line should look familiar to you. This is the T2 star. Again, my drawings are not great. I should have just used a text, but that is what you're seeing happening. Your spins are all going out of phase. That is your T2 decay right there. And with the free induction decay, it happens very, very fast. And so we don't generate a good signal that we can get anything from. We have to do something to bring this signal back to life later on, which you guys learned about yesterday. Do you guys remember the 2 ways we can bring this signal back to life to generate an echo? This one, it's okay if you don't know because you just learned it yesterday, but does anybody remember? Okay, so we can use an RF pulse. Okay, we can use an RF pulse to resurrect that echo. So we can use that in our spin echo sequence. It's a 180-degree refocusing pulse. What's the other thing that we can use to bring the echo, to generate that echo? In your gradient echo sequence, what do we use? Because we don't use an RF pulse. It's a gradient. Good job. So 2 things that you can use to actually resurrect this free induction decay and bring it back to life and generate an echo, either an RF pulse or a gradient. All right, what can you guys tell me about T1 recovery? Spin lattice, good. What does spin lattice mean? Oh, somebody already answered it, giving up their energy to the environment around them, good. When 63% of the spins return to MZ, the time the hydrogen protons realign back to be 0. How long it takes fat to recover. This also is how long it takes fluid to recover. There's a T1 relaxation for both of them. Good job. So as some of you said, this is when nuclei are giving up that energy to the environment, to the surrounding tissue, known as spin lattice relaxation. It has occurred when 63% of that longitudinal magnetization has recovered. And as some of you said, this is referring to that NMV relaxing back to the Z-axis. That is T1 relaxation, just the relaxation back. What can you tell me about T2 decay? Okay, spin, spin. 63% of the spins have dephased into the XY plane. Good. Dephasing. Good. The time it takes for hydrogen to dephase. Good. You guys nailed them all. So again, spin, spin is when those nuclei are exchanging energy with each other. This is that dephasing in the transverse plane. Those watch faces are now all facing different directions. So we are not cumulative. We're not getting any signal from that. When the RF pulse is turned on and applied to the hydrogen spins, are the spins in phase or out of phase at that point? So RF pulse has been applied to the NMV. Are the hydrogen spins in phase or out of phase at this point? Yeah, they're in phase. Okay, so when that RF pulse is applied, it is like a punch to all of those hydrogen spins in the same direction. So it knocks them all into the exact same precessional frequency or precessional path. So when we turn the RF off, what happens? It's the T2 star decay, right? They start to fan out, they start to dephase, they start to lose signal. What is repetition time? Very good. Most of you got this too. So see, you guys are doing great. So this is the time from one excitation pulse to the next excitation pulse. It is measured in milliseconds. This determines how much recovery is allowed to occur between those RF pulses. What is that referring to when we say recovery? So it's determining how much of what can occur. Good, yes. So when we're talking about repetition time, time from excitation pulse to excitation pulse, this is referencing that T1 relaxation. How much time are we allowing the NMV to relax back to the Z-axis? So repetition time is in control of that. How much time are we giving the NMV to relax all the way back to the Z-axis? Typically, we want to give it time to relax fully back, but there are times we may not, but usually we're going to allow it to relax all the way back. So determines how much of that T1 recovery can occur. How much of that relaxation is going to occur. And this is referring to that spin lattice relaxation. Repetition time, controlling factor of our T1 weighting contrast. Okay, so see how it kind of all goes together. Your repetition time controls the T1 relaxation, and it controls your T1 weighting. Okay, those are kind of going hand in hand. Who remembers what is the repetition time for T1 weighting? What is the range? In numbers, what is the range in numbers for that T1 TR time for the T1s? All right, so we're about 50-50 split here. So I'm going to go back to this for a second. Look at this diagram, okay? RF pulse to RF pulse. Do you see how the spacing is between those two? Now look at your RF pulse to the time of echo. Notice which one's much smaller. Your echo time is always going to be tiny in comparison to your repetition time. Okay, even your long echo time is still tiny in comparison to your repetition times. So your smaller number when you're giving me ranges is always going to be the echo time, okay, of the two. Some of you are getting them confused a little bit. So just remember, echo time is always going to be the smaller number of the two that you're giving me between the repetition and the echo time. So repetition time for a T1 is going to be 350 to 800 milliseconds. Usually you're going to see 400 to 800, but you can go as low as 350. You will not go below 350 otherwise. So 400 to 800, 350 to 800, and you never go over 800 because guess what? When you go over 800 milliseconds, what happens? What's going to happen if you go over 800 milliseconds? Who knows? Remember what repetition time controls. So if you make your repetition time longer than 800 milliseconds, you're going to lose your T1 weighting. You're going to lose it. And you're going to start to go crossover into that gray area where you're transitioning from T1 to T2 or proton density like. So you must stay below 800. What is the repetition time for a T2 weighted image? What do we want if we're doing a T2 weighted image? So T2 weighting is over 2000 milliseconds for a repetition time. It's long. So you want over 2000 milliseconds. You may see it go as low as 1600, but typically it's over 2000 and usually stops around 6000. All right, proton density. What would the repetition time be for the proton density? Remember, proton density, we want to minimize T1. So what are we going to do to minimize the T1 weighting? You got it, over 2,000 milliseconds again. So it's going to be similar to your T2 weighting when it comes to the repetition time. All right, what is the definition of echo time? It is the TE, but what is the definition of TE? All right, good. So yeah, it's time from the RF pulse to the signal that's induced in the coil, the readout of that echo, hence the name echo time. It too is measured in milliseconds, and it's going to determine how much decay is to allow to occur between the application of that RF pulse and that signal being read out, which means what? What are we allowing to occur? What are we referencing when we say we're talking about how much decay is allowed to occur? What's happening? Think back to repetition time when we talked about what do we mean when we're allowing so much relaxation to occur? And it was talking about T1 relaxation, that NMV going back to the Z-axis. Well, now we're talking about echo time, and we're talking about how much decay is allowed to occur. What is that really talking about? Okay, some of you got this, some of you got it. So it's how much we allow those spins to dephase. So echo time is controlling how much we allow those spins to dephase. Obviously, our best signal comes when they are all in phase together. But echo time is simply how long we allow those spins to dephase. It is also the controlling factor of the T2 weighting. So again, notice how they're going hand in hand. Okay, T2 decay is what we're actually utilizing here. How much T2 decay are we allowing to occur? And it controls our T2 weighting. So now we have T2 and T2 going together. So notice that they go together well. Might help you remember a little bit about it with the echo time. Echo time for a T1 weighted image, what would that be? Y'all are going to feel like your brains went through the meat grinder tonight with all these questions, aren't you? It's good though, because you guys know a lot of this and you can see now how far you've come in just a week's time. Remember, echo time is always going to be the shorter number when we're talking about referencing the repetition time and the echo time. Echo time is always the smaller of the two numbers. So echo time for T1 weighted image is going to be typically 5 to 30 milliseconds. You're usually going to see 10 to 15, but we can go as high as 30. But most of the time you're going to see 10 to 15. How about for a T2 weighted image? What will our echo time be then? It will be long, but what is that range that we're looking to fall into? So 80 to 120 milliseconds. You may see as low as 70, but 80 to 120 milliseconds is the range we're typically looking to fall into for our T2 weighting. All right, how about proton density? Last one. What's our echo time going to be for a proton density? Okay, good. If you said anywhere between 5 to 30 milliseconds, you are correct. All right. How many Tesla is in a 30,000 gal scanner? Easy conversion, right? You guys are all answering it like so fast. You are correct. It is 3 Tesla. This was not hard enough of a question. How many gals are in a 1.5 Tesla scanner? While you guys are answering that discussion forum for this week, if you did not make the class, since it is a review kind of class this week, what I want you to do is just write 2 paragraphs about whatever you thought was important during this lecture that maybe you know, struggled with last week and you found that you understood it better this lecture. Just 2 paragraphs highlighting the important topics of your choice for this week. Remember, 2 paragraphs should be 200 words at least. And reply to a fellow student by Sunday to make sure you get your attendance credit for this week. And you guys are correct. 15,000 gals. You have got it. Whoops. And then I apparently got carried away with moving that screen. What type of radiation does an MRI use? Notice there is a red check mark on this one as well. It is electromagnetic radiation. Also, when we talk about if it's ionizing or non-ionizing, which one is it? Good. So it is low energy, non-ionizing radiation, which is fantastic because it means it's not one of the cancer producing radiation levels that we use. While the RF pulse are the non-ionizing radiation, remember they can cause tissue to heat up. And what is that called when they cause tissue to heat up? SAR, good. And SAR stands for what? I'm gonna make you type it out, see? Specific absorption rate, excellent. Oops, I'm answering a question in the chat. Give me 1 second, guys. All right, frequency of radio waves. So when we talk about frequency, it's basically the wavelength. A wave completes 1 cycle when it returns to its original point of origin from where it started. The amplitude of the wave, okay, that's how tall the wave is, determines the power or strength. The radio waves we use, of course, are RF pulses. They have a frequency that is comparable to the range of microwaves or cell phone waves. They're in the range of millions of hertz or millions of cycles per second. For a 1 Tesla scanner, again, this number keeps coming back to haunt you, 42.58 megahertz. We must match that precessional frequency. All right, let me write down this. All right, remind me, what produces a free induction decay? We talked about this earlier. Who remembers? Good. It is the RF excitation pulse, not the refocusing pulse. I don't want everybody to think a refocusing pulse is going to cause one of these. It's not. It is that initial excitation pulse in the start of the sequence. Now, of course, that sequence is going to repeat multiple times. And so we're going to produce a free induction decay with every excitation pulse that we produce. When we are looking at this excitation pulse, what is occurring here? With my beautiful drawing, what is occurring there? T2 star dephasing, T2 decay, T2 relaxation, whatever you want to call it, that is what we're seeing happen there. That signal is rapidly decaying. That's that dephasing of the spins. All right, couple questions from week 1 that I thought that was a struggle on your quiz. Again, I think it's just wording, so remember to take your time. We try to trick you, and we do that with good intentions because your registry will try to trick you. It will say something, and always it's instinctive for us to just pick out choice words and instinctively respond. Make sure you're dissecting down the questions. What type of elements isotopes can be used in NMR spectroscopy? This one really stumped Amri. Yes, I do agree. Somebody said they can't take their time when they're being timed. I get that. But remember, your registry is timed, so we're trying to prep you for that. Not specific element. I'm not asking about the specific element. You guys are giving me the answer from the quiz. But what type of elements? You don't have to give me a name of an element. What are we looking for in particular? Yes, radioactive is an isotope, but what type can be used? See, somebody got it. Okay, there we go. Couple of you are getting it now. It's really dissecting down the question. Think about why we said MR active nuclei are utilized. If it's being used in MR, it's for the same purpose because it has that odd atomic mass number. So any element, doesn't matter if it's radioactive, doesn't matter if it's being used for spectroscopy. If it has an odd atomic mass number, that's what you're looking for. So if you're given an element with a 13, you're going to pick that over an element with a 14. It was just a tricky question because you're being asked about spectroscopy and you're probably thinking, holy crap, I haven't learned anything about that. Why are they asking me about that? Because it trips you up. That's it. Because we want you to look at the question and really try to find, what do I need to know? Because the registry will do that to you. All right. What do atomic nuclei contain? This one. Oh, yep. Go ahead. Was somebody going to ask a question? I heard somebody pop on, but maybe not. Might have been accidental. All right. Atomic nuclei. What do we find in the atomic nuclei? Which we did talk about already in class tonight. Yeah, it's protons and neutrons. Some of you silly gooses said electrons. They're not in the nuclei. They're not in the nucleus. But I think, again, the way the question was worded, we're kind of thinking of everything. What's all in that entire atom, in that structure? So protons and neutrons will be found in the nucleus. All right, couple things real quick. Some more of the stuff that you need to know for that mock interview coming up so that we can keep building on it. And I gave this to you previously as well. Remember, repetition time controls T1, go time controls T2 weighting. How does a T1 weighted image appear? Explain to me fat versus fluid. How do they appear? Okay, T1 weighting is going to be dark fluid, bright fat. Dark fluid, bright fat. That is your T1 weighting. How does a T2 appear then? Good. Bright fluid, dark fat. Make sure you 110% know this because you're going to be asked to identify pictures, images. It might be brain images. It might be spine images. Who knows? And we're going to say, what weighting is this? And you need to know that when you look at that fluid, if it is bright, it is T2. If the fluid is dark, it is T1. What is a stir sequence? Let's pull this out from last night. What is the stir sequence? What does stir stand for? Let's start with that. Okay, stir. Does anybody know what stir stands for? STIR. There we go. There's a couple. All right. Short tau, TAU, inversion recovery. IR is one of the inversion recovery sequences. Now, a lot of you were saying it's going to void fat and fluid. That is not the case. There are two inversion recovery sequences we use. One voids fat, one voids fluid. Which one is this? Good. Yeah. This is going to void the fat and all the signal from fat. It's dependent on that relaxation time, okay, of the fat. So your T1 relaxation, so that inversion pulse is applied, flips it 90 degrees. Then you apply the excitation pulse to flip it the remainder of the way into the negative Z-axis. And depending on how quickly it's relaxing, depends when we hit it with that actual excitation pulse. So STIR is short tau inversion recovery. I will actually type it into the chat. You need to know this. This is one of the big ones. Short tau inversion recovery used to null the signal from fat. We use this in a lot of our bone imaging. FLAIR is fluid attenuation inversion recovery. Somebody was asking about the FLAIR. So fluid attenuation inversion recovery. I will put that in the chat as well. Okay, that's going to void the signal or null the signal from fluid. But STIR is really the one I want you to be confident in. So short TI inversion recovery, short tau inversion recovery. You may hear both of those used to null the signal from fat. All right, guys, you are free to go. Unless you have a question, I'll hang out. Otherwise, I'll see you next week. Please remember, deadline is by Sunday, 11:59 p.m. for everything. If you're making up anything from this previous week, please get it in because we're going to close out pretty soon of all of that. But yeah, have a great weekend.